Okay, so just before the class, where it is, yes, just before this class, we saw about some rotations and stretching, isn't it? Yes. Well, for stretching, if you need stretching, what you do? Hmm? Yes. Use diagonal matrix. That's good. So let us see, let us properly analyze what is happening here. Okay, let us properly analyze what is happening here. Okay. See, this is the first step. Where is my pen? Hmm? Okay. So I see the first image. Carefully see the first image. See the colors in which they are distributed. Red is in which side? Red is on which side? Red is here, right? Red is on the right side. Hmm? This is the first step of the image. This is the second step. Okay, this is the third step. And this is the fourth step. Now we want to analyze. Now we want to analyze how you go from 1 to 4. Can you tell me how you go from 1 to 4? So observe that it has been stretched, first of all, and it has been definitely rotated. It has been rotated. Okay, to understand how we transform from 1 to 4, follow my steps. First, we go from 1 to 2. We go from 1 to 2. From 1 to 2, what has happened? What has happened? See, that the same, it is not the same circle, right? It has been rotated. See the red point. He is here, but now the red point is here. Isn't it? So it has been rotated. It has been rotated along this direction, right? How many of you agree? Yes, it has been rotated along clockwise direction. Yes. How you achieve it? You achieve it via a rotation matrix. Via rotation matrix, right? So from here to here, rotation is done. Next, let us go to 2 to 3. From 2, how you go to 3? Does it change? Does it rotate anymore? Because the red is staying at red. Any point you take, blue is staying in blue position. But it is getting stretched. Is it stretched only in one direction? What do you think? It's difficult to tell. It's difficult to tell, but it is being stretched in both directions. It has been stretched along this direction. Something has happened. So yes, it has been stretched along this direction, and it has been stretched along this direction as well. And that resulted this circle to get into this ellipse. This ellipse. Okay. Now let us go from 3 to 4. So from here to here, you told me it is stretching, right? Yes. Now from 3 to 4, how you will go? 3 to 4, you have to rotate this along which? How you will rotate this? How it has been rotated, do you think? It has been rotated, I think, on the clockwise direction through a big angle. Like previously it was this, it has been shifted to this angle, like it was a big angle, right? Yes. So you can see this red point is now coming here. Okay, so it has been rotated like this. Okay. So from here to here, it is rotation. Okay. So you can see that as a whole, like as a whole from step 1 to step 4, if you want to go from step 1 to step 4, you have to do 3 operations. One is rotation, then stretching, then rotation. Okay, rotation, stretching, rotation. Yes. So if you apply rotation, stretching, rotation, you can go directly from 1. Okay, that's the step. That is exactly what singular value decomposition does. So here I have written it down. You can see now why I have written this matrices here. So to go from this 1 to this 2, like A to B, from circle to this sign here, ellipse, rotated ellipse, you have to first do the rotation by theta, some angle theta, yes. Then you did the stretching. Stretching means you have to use the matrix, sigma 1, sigma 2 on the diagonal matrix, yes. So you know that it will stretch on this side as sigma 1, on the vertical side as sigma 2. Fine. Yes. Then the third is rotation by phi. Rotation by phi. Like another rotation was there, right? Remember the sequence, no? Rotation, stretch, rotation. Yes. So this one is clear to you. Okay. Let me tell you something. Yes. So this is exactly what SVD is. I told you in the, here I have told you. This is what exactly SVD does. What SVD does? Singular value decomposition. It given a matrix A, any matrix, it can be any matrix, rectangular matrix, square matrix, any matrix. It will decompose the matrix A into product of three matrices. Matrix is an orthogonal matrix, that is U, okay, that is a rotation. Then sigma is the diagonal matrix that will do the stretching for you, stretching, or maybe we can say scaling actually, to avoid just stretching. We can use scaling because scaling involves both stretching and shrinking. Yes, sometimes if sigma 1 is less than 1, it will shrink. If sigma 1 is greater than 1, it will stretch. Yes. So this is the stretching matrix or scaling matrix sigma. And this is a diagonal matrix where the diagonal elements of the matrix will be the singular values, not the eigenvalues. Therefore, since it is singular value decomposition, the entries are singular values. Okay, the diagonal entries are the singular values. Okay, and then we have this V transpose. V transpose is another matrix which does the rotation again. Okay, don't worry about this transpose. Some books you might see this is a dagger, like some notation they will do dagger. So just to make sure that this is both rotation matrices, okay, but it's just following the notation. There is no much interpretation about this, why the dagger is used or why transpose is used. It's just the notation people have been using. Fine. So this is what SVD does. This is what SVD does. That's all. Okay. Singular value and then decomposition. That means singular value decomposition. What does it mean? You decompose the matrix A and extract the singular values out of it. Okay. So you decompose the matrix A and you extract the singular values, that is sigma, out of it. Okay. So it is a bit tricky to do it by hand. SVD is usually been tricky to do it by hand. You can do it. Is this closed? Okay. So yes. So we will see how Python can be used to do SVD operations. Okay. So this is how it is. Take this matrix A, 3, 0, 4, 5. Of course, it is a square matrix, but we will see that if it is a triangular matrix also, rectangular matrix also, it is not a problem. Okay. So how we do it? We write A equals to A is being decomposed into this U. This is sigma. This is V transpose. These are the products. These are the products. Okay. This is U. This is a orthogonal rotation, orthogonal matrix, orthogonal, and a rotation matrix. This is our scaling matrix, scaling but diagonal matrix. This is again rotation matrix, rotation by phi angle, and an orthogonal matrix. Okay. I will tell you, I am just telling you the steps right now, but we will dive into more detail after you understood this concept. Okay. So you can do this in Python as follows, like import numpy, and then from lin ALG package, you can import SVD. Okay. Then just do define your matrix A over here, which is 3045 for this case, and just do SVD of A. Just do SVD of A. Similar to QR of A, similarly you do SVD and call, and input will be the matrix A. Okay. Then what is the output? What is the output you get? You have given the input. The output you get is follows. This is U. U is the matrix which you see here. Okay. This is a rotation matrix, an orthogonal matrix. Okay. You can clearly see that when you take the dot product of the two rows, you will get 0. Okay. It is very easy to see. This is the first row. This is the second row of U. Okay. Take the dot product and convince yourself that it is a orthogonal matrix. Okay. And this is sigma S. This is the diagonal matrix. Okay. And since it's a size 2 by 2, it is giving you two singular values. Those two, see, these are singular values. These are singular values. Okay. Fine. And it also gives you the V transpose array, VH, okay? V transpose array that is combined of these elements. This is again an orthogonal matrix, a rotation. Check again, this will be orthogonal for you. The dot product again will be 0, okay? So when you do SVD of A, it gives you all these matrices. Python gives you these matrices, U sigma and V transpose. It's okay? How many of you it's difficult, did not get? Yeah, so this part is okay. This part, like U sigma V transpose. I mean this part. Which one is difficult? The Python one. Yes. So what you do here? Let me zoom in here. Yes. What we do here, you define the matrix A, whose SVD you need. Through this definition, can you see that A is 3, 0, 4, 5? Okay for you? Yes. Then what you do? You apply SVD of A. SVD is a function, and you input matrix A into it. And what output you get? If you do this, the output you get, the output of this is 3 matrices, U, sigma, V transpose. It will give you those 3 matrices which you multiply, get A back again. But these matrices are special because this U is an orthogonal matrix, does the rotation. This S is a sigma matrix that is consisting of all singular values. V transpose is again an orthogonal matrix which does again the rotation. Hope it is clear. You are not able to see how it is a matrix, right? The output. I think I will write it. U is just this matrix. Can you see it now? U is this. This is orthogonal matrix. Why? Take the dot product of any row, 2 rows, it will be 0. See, minus 0.3162, this is plus 0.3162. This is minus 0.9486, this is, yeah, negative again. Okay. And what is sigma? Sigma is written as S. This is this array, 6.7082, 2.2360600. V transpose, minus 0.7071 something, and then minus 0.7071 something. Then what is there? Minus 0. So same, all are same. It is also an orthogonal matrix. Yeah, I did a mistake. Yes. Okay. So for this matrix A, that is 3045, convince yourself that when you multiply U sigma V transpose, all these 3, you will again get A. So this is what the singular value decomposition is useful for. Okay. You got it? So yeah. So this is one intuition of geometrical intuition. This we will see in Python again. This we will see in Python again. We have a code for this, and I will show you that it actually does this transformation. Okay. Okay, before we do, okay, so take a look into this matrix. Take a look into this matrix, which I have just put a star mark. 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, 2, 4, 6, 8, 10, 20, 30, 40. Okay. Can you see something happening here? You can see that if you just take this matrix, this row here, 1, 2, 3, 4, okay, and just do a negative, just multiply this vector with itself by 1, you will get that vector, fine. If you multiply the first vector with minus 1, you get the second row, okay. You multiply the first vector by 2 and you get 2, 4, 6, 8. You multiply the first vector by 10 and you get 10, 20, 30, and 40. Yes. So what you get? The whole. So how many numbers are here? 16 numbers. isn't it? How many numbers are here? 16 numbers, isn't it? Yes. But you can actually store this whole matrix. You can actually store this whole matrix in this way, as in this way. Like you can see 1, -1, 2, 10, and 1, 2, 3, 4. Okay, 1, 2, 3, 4. How many elements are required here? 8. So you can see that suddenly I reduced the complexity by 50%. Okay. Previously, 16 numbers were needed to describe this matrix, but I now only need 8 elements to describe this matrix. What I will do, like this is how I read this matrix. Technically, it's not that equal. Like 4 cross 1, this is 1 cross 4. Okay. So you can feel it, right? Can you feel what I'm trying to do it here? Yes. How many of you did not understand? Everyone understood. Okay, so the idea is you had this array, this matrix A, and this is a size 4 cross 4. That means it has 16 elements. It has 16 elements in it. What I'm saying to you now is this matrix is something nicer. Because the first row, just keep in mind the first row and the first vector and remember this vector, then you can entirely reproduce the matrix A. Just by using 8 numbers, you can reproduce the matrix A. You don't need 16 elements. Is it good? Previously, you were storing 16 elements, you are having more memory. Now you are doing the job with only 8 elements. Is it? So that is efficient, no? Isn't that efficient? That is efficient, yes. Because you can just write this 1, -1, 2, 10, and 1, 2, 3, 4. And just by these two vectors, you can entirely reproduce the matrix. So that's how you do this compression of data. This is what compression of data looks like. Okay. Previously you needed 16 numbers, but now you needed 8 elements. Okay. Just by multiplying vectors. This is one vector, this is one vector. That's it. That's it. See the orientation of that. See the orientation. This is a chunk. This is a fat chunk. But these two are something like this. Remember the orientation. This is one long mastic. This is a horizontal mastic. This will come again and again repeatedly in the few slides. Okay. Okay. Fine. Now let us see this below matrix again. 3, 1, 4, 1, 5, 9, 2, 6, 5, 3, 5, 8, 9, 7, 9, 3. Can you write something like that? Can you write these 16 elements? This is also 16 elements. Can you write something like above? Do you think? Not that easy. The above matrix was very nice. You could just multiply and get something out of it, and it was very easy. But the second matrix is not that easier. Second matrix is not that trivial. Second matrix is not that trivial. Okay. All right. So this is what I meant by this. Can you find the rank of this matrix? What is the rank of this matrix? What is the rank of the matrix? 0. Are you sure? Why? Why are you saying it is 4? No, this is rank 1 matrix. This is a rank 1 matrix. 3 rows you can write. 3 rows you can write based on the first row. Isn't it? All 4 rows you cannot write. 3 rows you are writing based on 1 row you are comparing, right? How many rows you are comparing like that? 3. So 4 minus 3, that is 1. So how many, what is only the element remaining? 1. Based on that one element only you are comparing. Can you actually do some other operations? Maybe you can do row echelon form or something, but convince yourself that rank is 1. Rank of this matrix is 1. Rank 0, I have not seen actually. Rank 0, maybe some search now. Search. But I don't think rank 0 will be there. Rank 0 is very unusual. That means you are saying 0 linearly independent rows. 0 linearly independent rows. Can it be? Can a matrix have 0 linearly independent rows? When all elements are 0 in a matrix. Yeah. I think so. Then it is possible. Can you do some research now? Do some research. That is a good question. Do some research. Let us learn. Okay. So this is a rank 1 matrix. This matrix. Okay. Since it is a rank 1 matrix, you can decompose into like this. You can decompose them into this kind of vectors. That is one column vector and then one row vector. Okay. These are known as rank 1 approximations, and these are very important. These are known as rank 1 approximations of a matrix. Okay. This you might see very easier. I think in machine learning SVD is very common. Okay. But directly they start with u A equals to u sigma B transpose. That's it. Okay. Anyway, so what is this idea? Can you tell me? To decompose like this matrix should be of rank 1. Is this of rank 1? We don't know yet. We don't know yet. We will see. We will see. Think about this. Okay. So this is what it is. This is what it is. This motivates us to rank 1 matrices. Okay. So given a matrix A, this is a matrix A. Okay. Now, if this matrix A has a rank 1, then you can decompose them into this sort of ways. Okay, this sort of ways. That is, matrix A is equal to this plus this plus this, and so on. That doesn't stop here. It can be any terms you like. It can be any terms you like. Okay. So what is this term? And what is this term? This is a vector v1. Okay. Maybe it will be clear if we consider some examples. Maybe this one. Okay. So you can write matrix A into U sigma V transpose, right? These are the products. This is U. This is U. The matrix U looks like this. Think of matrix U as a collection of matchsticks. As a collection of matchsticks. Matchsticks are like vertically located. Okay. Fine. And then this is U1, U2, U3, U4. This is what the matchstick you look at. These are the tall vectors you look at. Okay, each U1, each vectors is here. Okay, U1, U2, U3, U4. Okay, then you have the sigma 1. These are the singular values, right? I told you about. These are singular values. This is a 3. This is a 3. So singular values. These are singular values, and this gets multiplied over here. This gets multiplied over here. Okay. Then V1. V1 is the horizontal mastic. Okay. U is the vertical mastic, and V is the horizontal mastic. That's why you can think that if you just remember one, that U is a vertical mastic, then by the notation of V transpose, you can think that the mastic vertical is being transposed, that is horizontal mastic. Okay with you? Okay with you? So therefore, this A can be written as this guy plus this guy plus this guy plus this. So what are we doing essentially here? We moved one step more. Actually, we moved one step more. Can you understand? See, this part you already know, right? Before the break, you already know about this. A is transformed into U sigma V transpose. You already, before the break. But this is something, this step 2 is something new for you. Okay. And this you can only do, you cannot do every time. You cannot do it every time. You can only do when rank of A is 1. Okay. When rank of A is 1. Okay, therefore, my title above was approximation by rank 1 matrices. And why sir is saying approximation, even though sir is putting an equal to sign? Why it is an approximation? This is where the twist for data compression actually comes. Okay, this is the tool where data compression actually comes. See, A is written as 1, 2, 3, 4, right? 4 sums. 4 sums are there. Is it okay? How many you could see that 4 sums are there? Raise your hand. How many of you can see that 4 sums are there? What happened to this? What is the issue? You should ask, else it will be very difficult. Like later you won't get it. What is the difficulty for now? What is the issue now? What is the issue? Second part. Okay. You already know that a matrix A, this, can you feel that this is a matrix A? Now, can you, I just told you that you can write as a product of this vertical matrix and a horizontal matrix. And one is multiplied here, isn't it? One is multiplied here. Now, a matrix A can be written as something like this, a big vertical basket, a vector, and then a horizontal basket. Yes. Now, the same I am doing here. Vertical basket, horizontal basket. Okay. And how many times you can do it? How many times you can do it? You can actually write, it depends on this U matrix. It depends on this U matrix. Okay. U matrix is comprised of these vectors U1, U2, U3, U4. And V matrix is combined of these horizontal rows V1, V2, V3, V4. You just have to take each of these like a Kit Kat. Just take it like a Kit Kat. How many Kit Kat rows are there, columns are there? Break it and put it. Isn't it? That's what you do, nothing else. This is one Kit Kat you borrow, break it. Mr. Aman break it and he kept it here. Okay. Then you break the green one and you kept it here. So on it went like this. And how many times you will do? How many times can you do this for infinity? No. Why? Because you only have 4 of them, right? So you have to go till 4. You can't. Is there U5? Is there U5? No. Therefore, I did not write U5. So only this is there. Nothing else. Understood? Understood, Mr. Jubin? Mr. Chaku? Understood. Last. You again went there. Such a special sheet we have made. Yes. So are you convinced? Are you convinced that a matrix A can be written like this? Are you convinced? You can only do this. You can only do the step 2, not in any matrix. You can only do when rank of A is equal to 1. Only when rank of A is equal to 1, you can do this. I gave you an example. Rank of A in this case was 1. Then only you could do this. Right hand side. Okay. Therefore, when rank of A is equal to 1, only then you can break it down to this. If rank of A is not equal to 1, it is 2, 3, 4, you cannot do this. What you can do, I will tell you. But like this, you cannot break it. Okay. The structure will be a bit different. Okay. Got it? We will see. We will see. Maybe I wrote one example for you, right? You can see here this is U1. This is U2. Isn't it? V, you can write it as, this is V1. This is V1. This is V2. This is sigma 1, sigma 2. Okay. Okay. So this is what we do. Now what role? Why we need to do this complexity? Why we have to go to this such complex visualization? Only for data compression. Only for data compression. I will tell you why the data compression works. Okay. So see that sigma 1, sigma 2, sigma 3, sigma 4 are the singular values of the matrix. Okay. If sigma 1, sigma 2, sigma 3, sigma 4 are there, they are real numbers. So one of them will be greater. One of them will be the greatest, and one of them will be the smallest. Okay. Suppose sigma 1 is the max element and sigma 4 is the minimum element. Okay, min. And this is the maximum, this is a bit greater. This one will be a bit medium value, and this one will be a smaller, medium or smaller value. Okay? Smallest one. Fine. Fine. Now tell me, like, if you can write matrix A as this guys, matrix A as sum of these four sums, like this first part, second part, third part, and fourth. Okay. Now, how can you approximate A? How can you do in such a way that it will still look like almost like matrix A? Much of data won't get lost. Which element should you remove? Should you remove this first element or the last element? So remove the element in such a way that matrix A it will change. The element of the matrix A will change, but it should not change in a big way. It should change in a small way, like 3, one element is 3, it will change like 2.8. Then you can at least see that it is 3. Which part you should remove? Yes, that's good. That's good. You're working. Okay. So the last one you should remove. You can remove this one. Okay. So you can write this as the sum of this plus this and neglect this. If you neglect this, it can also work. But of course, you will lose some data, but your data will almost be compressed. Yes. So this is what is meant by the compression. Okay. So you decompose the matrix A into these 4 chunks. Okay. And then you remove the lowest singular value. Lowest singular values, thinking that it will approximate the matrix A. Are you getting the idea? What I am doing here? First, you write this as equal to, but then I'm telling you that even if you remove this guy, it will be, this 3 quantities is approximately equal to A. Approximately. So that is what the title meant, approximation by rank 1 matrices. Okay. So that means you don't need all the 4 chunks to store your data. The 3 chunks will also store your data, like in a good way. Okay. So isn't it a compression? Instead of 4 chunks, you need only 3 chunks to represent it. Isn't it compressing your data? How many of you think it is not compressing? How many of you think it is compressing? How many of you think it is compressing? What happened to those two? What do you think? It is not compressing? Come here. Come. This side, any doubts? This side, any doubts? Compressing? No, not compressing. Why not compressing? It's compressing. How many of you think not compressing? Third row, compressing. Why? Okay. Hang on, you are there. Okay, so this is where things get more interesting. Like if matrix A is of rank 1, then you can write it as vertical matchstick and a horizontal matchstick. Okay, like this. When this matrix A is of rank 2, then things gets interesting. Then you add club another KitKat bar and make it more. Okay, so you can see now we have padded another vertical line and another horizontal line here. Okay, but the structure remains the same. It's the vertical and the horizontal. It's the T shape. Okay. Similarly, when it is rank 3, when matrix A is of rank 3, you need to decompose in this way. 3, club 3 and club 3 here. If it is a rank 4 matrix, then of course you have to decompose it into 2 matrices, 4 cross 4, 4 cross 4. But this is not that useful. So usually things get interesting if you have a rank 1 matrix. So therefore rank 1 matrices are of utmost importance. Okay. So try in any of the applications, try to make the matrix to be of rank 1 and then do your applications. Okay, because rank 1 out of all these things, this one is the easiest. This one is the easiest, isn't it? Just one KitKat bar, one KitKat. Simple, finish. Okay, okay. Okay. I think I'll show you some Python examples. Some gun is going in. So this part, did you learn how to do this SVD? The first example you learned, right? Okay, now I'm showing you this one. Yes. So you can see that the first one is a unit circle, right? First one is a unit circle. Mark the points where the colors are. Okay, mark the points. Mark the points where the colors are. So where is the red color? Here is the red color on the right. Here is the red color on the right. Here is the red color on the right. Yes. Then after that, what happens? You apply the rotation matrix. Okay, the rotation matrix is something like this, minus 0.71. This is some, yeah, it's a orthogonal matrix, right? This 2 by 2 is an orthogonal matrix. Why? Take the row 1, dot product with row 2, it is coming out to be 0. Okay. But rotation, and you already know orthogonal matrix, what it does? It rotates. It rotates. Along what degree? How much degree will it rotate? This is an assignment for you to think how much degree to rotate. Okay. Convince yourself that based on these numbers only, it is 135 degrees. 135 degrees. Just y by x. Think along it like it is tan theta equals to -1. Tan theta is only -1 when theta is more than 90 degrees. That is 135. Tan 45 is 1. Okay. Fine. So if you do that, it rotates the matrix. It rotates the points. Yes, it rotates these vectors. Now you see it has rotated 135 degrees. So now the red point has come down. Previously, the red point was in the first quadrant, almost here. Now the red point after this matrix rotation has come here, which I showed you in the class, in the slides. Okay. Then what happened? Then you apply the stretching. And for that, you need a diagonal matrix, right? You see, this is a diagonal matrix, 6.71 and 0.45. 6.71 means it will stretch along the x-axis. X-axis rather than on the y-axis. Therefore, it is a bit flatter. It is a bit squished. It is a bit squished. Yes. It did not move up because 0.45 is the direction along which it will move. Okay. That is less. Fine. After that, what you do? After that, you again rotate it. Rotate it. So rotate this number, or this is again an orthogonal matrix. And you can this angle minus 108 degrees. So it has rotated by 108 degrees. So you can see you get this one. This is the final transformation. Okay. Fine. So yes. So this is one application to image compression I want to show. Maybe I'll tell now, and then consider some math behind it, and then Mr. Aman will talk something about this. Okay. Okay with you? Okay. So let me just quickly go through this. Don't worry about the code. I will not go through the code. And I don't expect you to go through the code also. Okay. Because it is a bit involved. The code is a bit involved in the sense that over the time you will get to know. And if you're interested, you can Google each line of the code and try to understand the meaning. Okay. But I will tell you the gist of it. I will tell you the summary out of it. Yes. So see, this is a matrix D. This is a matrix D. And this matrix is covered only with zeros and ones. Only with zeros and ones. And you can see that once the places where 1 is there, it is denoted by black color. And where it is denoted by white color. Okay. So I will quickly show this matrix to you, and then I'm applying SVD to it. Then I'm applying a function anyway. So I'll show how it looks like. Yeah. So it looks like the heart. Okay. Luckily, I did not do red, but black. Okay. So this is the heart. So you can see this. Yeah, looks like, but black heart. Yes. So you can see that you can just image by just putting zeros and ones. Okay. Black is denoted by ones, white is denoted by zero. Okay. So this is the matrix, and I am applying SVD to it. I'm applying SVD to it. What it does, remember the numbers. If you see below, I will scroll. Above the image, you will see a number. Above the image, you will see a number, and that number is the singular value of that matrix. Okay. As I have written. So what we did, we should remove the least singular value for data compression. Yes. Now you see the effect of these biggest singular values. Okay. Yes. So this is the 4.74. Okay, this is the 4 point. If you take the matrix with 4.74 singular value, that is the biggest one, you land up with something like this. Okay. And if you add up, if you take the second one as well, second singular value, that is 1.41, it looks like something like this. Again, 1.41 singular value, another value, it looks like this. 0.73, it exactly looks like the original image. Okay. 0, like 0 and 0, these are the least. So you can remove these two, isn't it? You can remove these two, right? These two singular values, and it will automatically compress your data, automatically compress your image. Yes, because even if you remove these two, there will be some change in your matrix, okay, in your image. So it depends totally up to you how much extent you want to compress your data. I can stop till here also. It still looks to me like a heart. The third image still looks to me like a heart. Of course, there are some noise here. You can see this one, some gray images, but this one is the perfect one. If up to here you take, it is perfect. Up to here, yes, the more compressed it is, the more compressed data is. So this is one example. This is, you can feel how matrices can actually play a role in image compression. Okay, you can clearly see I just created a matrix. I just created a heart out of zeros and ones. Okay, and then I am applying SVD to compress this data. Okay, and you can relate also that this is the biggest singular value. And how many singular values we have? 1, 2, 3, 4, 5, 6. What was the size of the matrix? Size is also 6. 1, 2, 3, 4, 5, 6. Yes, you can see it in action. Okay. So yeah, just play around with this code. The more change you do with these zeros and ones, your picture will look different. Okay. Try to make it across. Try to make it across and play around with it. Okay. Good. So another also maybe, yeah, this is the idea. Yeah, you can see this is U, this is sigma, this is V transpose. Okay. This is U, this is sigma. You can see all the singular values are on the diagonals. All the singular values. Okay. And the biggest singular value is 4.74. Lowest one is 0. So you can remove these two singular values. These two singular values. Okay. Another example also you can take. I changed the number of zeros and ones, the location of zeros and ones, and it gave me totally different picture. Something like this. And again, I am doing it, and you can see. Here, you can stop here also or here, up to you. But these three you can eliminate. The three things you can eliminate, and it reduces to it compresses your image. So can you get a feeling how singular value decomposition is used to compress data? I hope you are getting a feeling of it. Yes. Just not remaining in numbers. Something out of it. Okay. Fine. Fine. Okay, let us be back. Maybe I'll cover something you already know about SVD, and that will be end of it. And lastly, 10 minutes or something, Mr. Aman can show his application of SVD. Okay. So you're okay, right? You're okay with it? Just I think 10-15 minutes. Yeah, it will just, else it will be for the next week. It will be a break. Therefore, you're going with the flow, so just go with the flow. What? Okay. Okay. So now you know about a bit about singular value decomposition, right? Yes, of course, singular value decomposition won't be asked to you. Maybe next class we can do an example of singular value decomposition by hand. And that will be the most important example. Okay, you can expect it during your exams. Okay, so prepare yourself according to it. Read today's subject. Next class, I will discuss some theory today. Next class, first remaining half after the exam. How much time we have? Deducing minus of this. So we will do an example of SVD. After that, I think we will be, after that linear algebra is done, we will move to interpolation, interpolating polynomials and all those, like how to approximate functions and other things, okay, based on data. Interpolation, some signal things, Fourier and all, and that will be end, I think. What about the projects? What about the projects? Did they write everyone? How many are remaining? How many did not give? Raise your hand. Raise. How many of you did not give? I did not record. It was not recording. One should be responsible for this. The whole I told it was not recording. Anyway, I don't have any problem. It is you who will watch. You can send it to me, no? Just send the to mail. LLM. Give paper. Moodle I did not yet set. Did not yet set in my Moodle. It will take some time. Maybe I'll set it today. I'll set it today, but for now you can just give me. I will cover this in the next class. Remind me to cover this in the next class because it was not recorded. Someone will tell us something. Open. Yeah. So you can start explaining about the code. Okay, some lines of the code because it is simpler. And then, yeah. So wait. Just use this keyboard for now. Start. So it's one of the application of SVD. So initially what we are doing is, so hi everyone, my name is Aman, as you all know. So I am one of the students of DSES and I am teaching one of the application of SVD to all my batchmates. So let's start. So basically what we are doing is we having one image and we are trying to compress it using SVD, that is single value decomposition. So initially what we are doing is we are using one of the library which is PIL, and that PIL library we are importing image module, and it module is basically used to open an image. So we having one image scenery 3ml.png. We are just loading inside the open using a function which is defined inside image. So let's open it.
It's loading. File not found. Sir, actually, file is not in this PC system. Yeah. So now we have image as you see in the folder. So initially we are making use of PIL library, and from where we are extracting image module, and from image module we are using an open method to open the image. So basically that this method is not usually used to open image. Do not show. I will use another method. And then we have CV2 library, which is a computer vision library generally used for image processing and video processing task. So we are importing CV2, then we import NumPy as NP, then we have a visualization library, Matplotlib. So in CV2, we are using an image read method to read the image. So I define the figure size, access of, as I doesn't record access in this, and I'm converting this image to RGB, from BGR to RGB, as they by default take BGR. Let's run this code. So this is the image, original image, original RGB image. Yeah. So now I am applying SVD method on it. So I am trying to compress that image into a matrix. So I am using NP NumPy library, and from NumPy library I am importing linear algebra method, and from that method I am importing SVD algorithm, and SVD algorithm we are passing an image, and that image will be decomposed into the matrix. As you see, SVD, I am passing image. Now if I run the code, yes, yes, sir. It will first show. Yes, sir. It will automatically convert into matrix. See the power of the SVD. So matrix, or it can be image also, which you just downloaded. So you can see the first matrix, which is U, orthogonal matrix. It is of shape 720. What is 3? I think there is some mistake. Initially, there's the third value is the 3, but now it's showing 1280. I don't know why. So first represent the number of rows, second represent the number of columns, and the third one represent 3. Actually, 3 RGB values. It could be any values between. We having a range of RGB values. If I show you this one, U matrix. Image. Maybe server is taking time. maybe server is taking time in loading. That's why it's preferred to use on system intermediate. Yeah, it's coming. So it's U matrix. So we having how many rows? We having 720 rows. Actually, I just wrote, yeah, 720 rows, 1280 columns, and we having third values. Actually, these values, this one, it's 1 pixel having different values. Actually, it is just 3 values, but I don't know why it's coming 1280 and just 3. It's just a matrix, a row vector of 3. And 3 values represent RGB values, how much content of red value, green, and blue. So just 1 pixel. And we having first pixel, then next pixel in a row, then third pixel, 4 pixel. So we just compress an image into a matrix format. And these values are just RGB values. By fetch, no, first row. So these are some RGB values. I just forget about the same, but yeah, these are RGB values which range having some range, specific range to represent a particular color. Yeah, 0 to 455. Actually, I don't know. So what's my so in my system, the code is running something different, but here it's showing 1280. Initially, it's showing 3. I'm fetching the first row.
Everyone, it seems very new discussion what is going on RGB, what are these values. So try to Google it. Try to Google it. So in data visualization, you need to know about different colors. You need to know about the colors. So you can get anything depending on RGB. Computer can teach you that.
Yes, taking too much time to load. Because it's compressed the image into matrix, and that matrix is very large. So that's why taking time to. Yeah. Yeah. So we have a U matrix, S matrix, and V matrix. I just printed the U matrix and U matrix. They are different points. It's just a one row. It's looking like columns, rows. Just a one row, and one row having one this. This is just one pixel. This is just a single row. Now, usually it is very difficult to deal with the RGB values as we having a lot of values to store. So what we did is we are just trying to convert into grayscale image. So here I'm using that particular method or class from CV2 library to convert it RGB VGR value, which is by default to grayscale image. So I'm just converting VGR. So this grayscale image I convert. Then it's a combined code. And just a single code I showed you previously. And if you see first import numpy, matplotlib, CV2 library, computer vision, image read. Then I did convert to grayscale image. Then applied single value decomposition, which convert them into matrix. Now we are showing the shape and size of the matrix. And just, so it will just give us the image. I think it's not supporting some. Yeah, okay. So it's a Seaborn library where I just checking the importance of components. So here is the main task. Yeah, okay, okay. So we just providing some black scale, grayscale values, different components. As I told you, like we having U matrix. In U matrix, I am trying to provide slicing, all rows and all columns. And in third component, I am providing, as I told you, like in the third component, we are providing RGB values. But here we are providing black scale values, that is 720. So it will come here first. It will also come here, and it will also come here. So depending upon these components values, our image compression done. So first we having that original image, and I just reduce the component 680, 600, 520, 450, 350, 300, 200, 100, and till 1. While I reducing components of a color. So initially you see it's a clear image. I just compress second image, then third, and then fourth, then fifth, then sixth, then seventh, then 8, then 9, then 10, 11, 12, 13. You see, as I reduce the components, this image get diminished. So this is just basically application of SVD.
Okay, so at least you can get an idea, like